Today we'll be working on the following problem. Let f of x be a Lebesgue measurable real function on R. Suppose that we have a functional equation f of x plus y equals to f of x plus f of y for any x and y in R. Now we want to prove that f of x must be in the form of c times x for some c real number. Pause the video if you want to work on this problem by yourself. Okay, let's see how do we do this proof. From the conclusion, first f of x must be continuous, right? So, and then once it's continuous, then we can prove from the functional equation that f of x must be of this form, c times some x for some c. So first we want to show f is continuous. Okay, the only condition we know is it's a Lebesgue measurable, and there is a functional equation. So from the condition, it's easy to see f of 0 is 0, right? And also f of x plus h minus f of x is f of h. So in order to prove f is continuous, we only need to show f is continuous at x equal to 0, right? Once x is continuous equal to 0, from this f of x is continuous everywhere, right? So here now we need to apply Losing's theorem, very important theorem, which tells us the relationship between a measurable function and a continuous function. So from Losing theorem, we know there is a closed set E in R such that the Lebesgue measure of E is greater than 0, and f of x is continuous on E, right? So the original the general format of Losing theorem is like you can find some closed set E such that the measure of x minus E is less than a given epsilon, and then f of x continue on E. So now we can make this E a little bit bigger, smaller, right? As long as it has a positive Lebesgue measure and it's closed, and then f of x is continue on E. And then we can, actually it's not just continuous on E, it's continuous on E uniformly. Which means f of x minus f of y is, okay, which means for all epsilon greater than 0, this f of x minus f of y is less than epsilon when let's do this. for all epsilon greater than 0, there is some delta 1 greater than 0, such that the difference, because it's continuous uniformly, right? So f of x minus f of y less than or equal to if x minus y is less than this delta 1 and x and y are both in E, right? So for any epsilon greater than 0, then we have delta 1 greater than 0, such that this is that means f of x is continuous uniformly on E, right? So now we know this E has a measure greater than 0. Now from our previous problem, I think is a problem 6, we know this E minus E contain a open interval centered and a 0, contained in some minus delta 2 and delta 2, where delta 2 is greater than 0, right? We can make it this yeah. So now for all epsilon, now if we let delta to be the minimum of delta 1 and the delta 2. Now we can see like this, if x is in this interval minus delta and the delta in this interval, right? If x is in this interval, then x is in both E, so x is in E minus E, right? And which means x is equal to some like a y minus z, where y and z is in E, right? And now since y and z are in E, and y minus z is also in less than, because delta 1 is the delta is the minimum of delta 1 and delta 2, so delta is less than delta 1, right? So when y and z in E, and y and z of course also is less than delta 1, right? Now we have f of x, which is equal to f of y minus z, the absolute value. And then this is because of the functional equation, this is exactly f of y minus f of z, right? And now from here, from this condition, this is less than epsilon. What do we have? So if we go back, for any epsilon greater than 0, we can find a delta greater than 0, such that when x is in this minus delta to delta interval, f of x, the absolute value of f of x is less than epsilon. And we know f of 0 is 0. So this means, therefore, f is continues at x equal to 0. And again, because of this relationship, f is continuous everywhere, right? On R. Okay, so now the second part is pretty straightforward now. So f is continuous on R, and we can see like this, we want to see, find out what if p over q, the value when p, q integers, right? So basically we want to find out the value of f at the rational points. So if you think about this q times this from the equation, this is easily to see this is f of p, which is p times f of 1, right? So if we define c is f of 1, we can see like f of p over q is equal to, from this is p over q times f of 1, which is c times p over q for any pq in z. Of course q is not equal to 0, right? So this gave us like that is to see f of x equals to c times x when x is a rational number. Now because f of x is continuous in R, it's easy to extend this rational number to any number. So for any x, we can say like there exists like a Pn sequence goes to x, where this Pn Qn is just integers, right? And from 1 to now f of x is f of the limit, Pn over Qn, they're all rationals and goes to infinity. And because of the continuous, this we can swap the limit and the f. This become limit of f, Pn q sub n, which is times c, right? Because of this, and this is exactly, and then this becomes x, so cx. So for any x, that's it.